morning, everybody. Welcome. So I'm really happy to be here as a technologist to have this opportunity to talk to you guys, customers, face to face, on what I think is transformational, is the new memory offerings in the Agilex family. So I've been doing design and architecture of high-speed memory systems for most of my career in some form or fashion. And I started off doing them in ASICs, and I've also worked for some of the large IP companies. But it was 13 years ago I was enticed to the FPGA world. Originally to a competitor, and more recently here in Altera. And to be honest, I was hesitant because my experience with FPGAs, particularly around memory and I/O, was they were not as performant as ASICs. But I did make the move, obviously, and it's the best move I've ever made, because designing high-speed memory systems for FPGAs is incredibly challenging and extremely rewarding. You guys don't need just one DRAM protocol. You need all the DRAM protocols on the same I/O. At the same time, you want to drive an LED with GPIO on the same I/O. And at the same time, you want to do LVDS. Same time, you may want to do MIPI, and so on and so on. So this kind of leads me to my passion, and that is designing ASIC/SoC/CPU quality high-speed memory solutions for FPGAs. My other passion is ensuring that those solutions are performant. And so performant in the context of your applications in the FPGA. So whether it's PCIe or Ethernet or CXL or HPS or the fabric communicating to that memory through interconnect, it needs to be performed as a whole. And in this capacity, I also lead our performance modeling team. And I would say that our main charter of our team is to ensure that our FPGAs are meeting your performance requirements. So with that, I'm going to start talking about this trend over the last 10 plus years of the specialization of DRAMs. And I'm going to go into the key attributes that differentiate the different DRAM protocols. And hopefully that will help navigate you towards selecting the right DRAM fit for you. I'm then going to introduce the memory offerings of the Agilex family. Then I'm going to go into details on some of the architectural innovations that we have made there. Finally, I'm going to wrap up and bring us to Quartus and talk about the enhancements we've made in the EMIF tool, which is the external memory interface IP generation tool, to give you the best-in-class developer experience and shorten your time to market. And then I'm extremely excited to have Thomas Summers, serial entrepreneur and CEO of Positron AI, come up here. And he's going to talk about his Atlas platform, which is a transformer server, large language models applications. And he's also going to talk about the benefits of how Agilex memory have really differentiated that story for him. So DRAM specialization has gone mainstream. This is somewhat of an oxymoron, but it is fact. Traditional main memory has exploded into different parts. Retains itself. There is the high-capacity DDR. And so that's DDR3, DDR4, DDR5, and that's your traditional CPU and server memory. But we also see more prevalence of LPDDR. And LPDDR was originally developed for mobile, and it has crept into tablets, and then laptops, and more recently we're seeing LPDDR in the data center. I'd be amiss if I didn't mention graphics DDR, GDDR. To be honest, it does one job and it does it really well for graphics. It's still somewhat niche. But its bigger cousin, HBM, has really exploded in use cases. It was originally developed, obviously, for bigger graphics problems, but we're seeing explosion, obviously, in AI and crypto mining, high-performance compute, and so forth. And so it's pervasive in the data center today. So when you're looking at these different memory types, you really need to consider the various attributes associated with them. Capacity may be important to you. Generally, cost is important to you, and cost per bit. Performance per watt is important, and maybe just absolute power is important to you. When I mentioned shoreline here, that is in terms of the I/O usage on the FPGA to get the max use of the minimum amount of I/Os. May be important to you. Bandwidth is obviously important. And RAS, reliability, availability, and serviceability may be important. And footprint, your PCB footprint, especially in embedded applications, can be critical. So I'm going to present to you here a spider graph. And I've picked out 5 key attributes: capacity, performance per watt, RAS, max bandwidth, and inverse of cost or affordability. And so if you compare DDR5 to DDR4, you'll see the general trajectory we expect from JEDEC going from DDR3, DDR4, DDR5. There are some differences we'll get into later. But essentially, you're doubling capacity and you're doubling performance. And you effectively expect to get about 20% improved performance per watt. We'll talk more about that power later. In terms of cost here, I wouldn't really read too much into the cost here because it's ephemeral. I mean, right now, DDR5 may be crossing over in cost per bit versus DDR4. Now, if we go to extremes and compare DDR5 versus HBM, you're seeing that DDR, again, is the capacity play. Capacity, capacity, capacity. But HBM is just kicking it out of the park with bandwidth, performance per watt, and they are comparable on RAS, actually. Obviously, DDR is winning on cost. HBM is expensive, but you should consider your overall solution, your BOM costs, and your overall total cost of ownership, where it may make HBM make more sense versus DDR for your applications. Obviously, HBM is great for footprint with in-package memory. I love LPDDR. So I feel LPDDR is a nice sweet spot here. Obviously, LPDDR is great on power. We're going to see more about that. Yes, it's only 1/8 the capacity of DDR5 in terms of max capacity available, but it is 4x that of HBM. A lot of our customers love HBM, but they do run into those capacity limits on HBM. Now, finally, we want to consider other aspects such as PCB footprint. Obviously, HBM is great, but if you look at the LP devices, they're very attractive too. Today, you can get LP5 64-bit wide device of 4 by 16 channels in a single package. You put that on your board, compare that against DDR5 UDIM, for example. I/O shoreline, I mentioned this. The LP devices, if you look at DDR4, we used to have 26 I/Os for command and address. That is now shrunk down to 8 or 9 for the Gen 5 devices. And I'd be amiss if I didn't mention availability. A lot of our customers care about extended temperature range and industrial applications. And so LP4 is still dominant there. We are seeing it will move towards LP5. And to some extent, DDR4 as well, especially if you need to source your DRAMs from a tier 2 vendor. And finally, migration. If you're happy with DDR4, migration might be important. OK, so I mentioned all these attributes. There's a QR code here. Please get your phones out. And in your own words, we're going to do a word cloud at the end of this. In your own words, entering what is a really important key attribute for you, for your systems. OK, I'll move on. OK, I promised I'd mention power. If you look on the graph on the right-hand side here, it's presenting power for a 64-bit wide interface, such as a DIMM, or the LP packages I've described, which would be applicable for cache line accesses. And you're seeing, actually, DDR5 brings great performance, but there is additional power. It is gaining on performance per watt but in terms of absolute power, you are seeing a rise here. And you can see a bit of a shoulder there because the DRAM vendors are doing their best to push to more advanced technology nodes to get that power down. But if you look at LP5, it really is a winner. It's moving directly right with performance increase with flat power, which is really impressive. And what I need to emphasize here, which I failed to do, is we're talking about the device power, the DRAM power. We don't give that enough attention. And what you're seeing now with the latest technologies is your I/O power, which has always been dominant, is becoming less so. From DDR3 of 1.5 volts down to 1.2 for DDR4, 1.1 for DDR5. And then you go to LP5, it's 450 millivolts. Pretty impressive. So if we then compare LP in terms of traffic profiles are really important too. So I talk about page hits. So if you're purely sequential accesses and you're hitting the same page all the time, if you're 100% page hit. If you're purely random and you're jumping around your pages on your DRAM, maybe some form of random lookup, you're 0 page hits. What's interesting in LP is that, yes, LP5 is better on power, but as you go to random data, you show the impact of your traffic profile, which is really interesting. In fact, LP4 is quite comparable to LP5 in power. That's because LP4 devices are great devices in terms of efficiency under random traffic, especially on 64-byte accesses. On the right-hand side, we go up in speed. Everything here is ISO, and we're talking about 16 gigabit devices. So DDR5 5600 versus LP5 5500. We're seeing clearly that LP5 is winning on power here. So if capacity is not that important to you, performance is, or footprint is, LPDDR5 may be very attractive. So I've talked about all these various DRAM protocols and their attributes. So where in the world does a device exist that provides this flexibility and choice in DRAMs technology? Well, Agilex does. Okay, so I'll give you a minute to digest this while I actually brag a little bit. If you look at this, the Agilex family itself, I believe is the only family out there that supports 5 DRAM protocols. And if you look specifically on the Agilex 7 FPGA M series, it's probably the only piece of silicon out there in the world, FPGA and non-FPGA, supporting 5 DRAM protocols. It's also the first FPGA out there to support 1 terabyte of memory bandwidth. So if we start on the left-hand side here, we see on our Agilex 7 F and I series, we reach end-of-life DDR4. And then we have this step function, leap to the M series. And that's carried through to the Agilex 5 series, which is a mid-range series. That leap is due to a complete re-architecture of our memory, of our I/O bank, which we call an IO96B. I'm going to talk a little bit more about that shortly. I would say, though, as you look over the Agilex 5 devices, you're going to see from the left-hand side, we're going from lower power, lower density, lower cost to your higher mid-performance range. And you're seeing variation in your DRAM speeds. This is due to special binning that we do to get your power down, and also voltage scaling, and also to reduce cost and package choices and so forth. Let's talk about IO96B. So one thing I tell my team, it's a bit of a simplification, but essentially our customers pay for logic elements and IOs. And by golly, they should be able to use as many of them as possible. And so a lot of the emphasis on this new architecture is to maximize our pin packing efficiency. So the IO96B bank is 96 IOs, but we split it into 2 voltage domains to give you that voltage selection capability. And then across the bank, you can mix DDR, Phi-Lite, MIPI, LVDS, and GPIOs. And you can see on the right-hand side here, there's a mock-up illustration of an application in a single bank that's doing 2 by 16 LP5 channels. It's doing 4 lanes of MIPI D-Phi, and we still have some IOs left over to push in some GPIOs. If you look down the bottom, this mock-up, you're going to see the two controllers, the hard memory controllers, HMC, we have two independent controllers, one 32-bit wide, one 16-bit wide. These are world-class controllers. We provide 32 deep queues, these controllers. This is required based on our performance analysis of DDR5 and the doubling of banks every generation. It's imperative that you need this depth. And compare that to competitors, particularly soft controllers. You'd be hard-pressed to get a controller with more than 4 deep queues because they're extremely expensive to implement them in soft logic. A big standout of our controller is we natively, as you can see, support dual channel by 16. And you're going to see later on that you get way better efficiency going to narrow channels on these LP devices versus wider. And so a dual by 16 is preferable against a single by 32. The competition generally only offers single by 32 interfaces for most of the devices. It varies a little bit. In addition, we are moving to AXI 4 for all of our interfacing. And our i96B offers both direct fabric access, which if you're familiar with competitors Versal, they've introduced a NOC on Versal, and the only way to access memory is through that NOC. We've heard these complaints, and so we make our i96B accessible both through traditional fabric and through the NOC. The new protocols introduce per bank refresh, so those refresh penalties you've seen in the past are, for the most part, hidden, particularly with this world-class controller or controllers. And then we have extensive RAS and debug features. Clearly, obviously, we have ECC, SecDed, single error correct, double error detect. But LPDDR5 and 4 also provide inline ECC. We've seen a lot of customers struggling with LP without ECC in the past, but there is a performance hit with inline ECC. So LP5, in addition, provides on-die plus link ECC as part of the protocol. We support ECC writebacks and on-demand scribbing. And one feature which I think is going to be extremely valuable for customers is the controller plus DRAM BIST. So controller is capable of generating complex traffic and pushing that all the way to DRAM and reading it back from DRAM. And in situ, in your system, when you have it up and running, you can go through the debug toolkit to immediately isolate issues, whether it's on your board, whether it's a misparameterization of the controller, or it's in your fabric. We also support multiple telemetry counters for performance debug. And finally, we support dual rank UDIM, RDIM, and SODIM. Okay, I've mentioned channelization. More channels, more banks equals higher effective throughput. DDR5 is a bit of a paradigm shift, actually. DDR5 is the first DDR protocol to split the DIMM into 2 channels. We're going from DDR4, single channel by 64 plus ECC, to dual channel by 32s plus ECC. So you see on the right-hand side here, you get 2 40-bit channels if you count ECC. And the result of this is 2 extra channels, 2 extra banks. The effect is more than a generational uplift. This is a quote from Micron. And data shows that at ISO performance, on the left-hand side here, you'll see DDR4 3200 versus DDR5 3200. You're seeing 36% more effective bandwidth on DDR5 on certain traffic profiles at ISO performance. And from modest data rate increases, you're getting significant performance increases on DDR5. I mentioned channelization on LP. This is LPDDR4. This is our performance for dual by 16 versus the competitor's single by 32 channel. And this is published data from the competitor. We're over 2x in terms of performance. And this is random data. This is pretty impressive. This is where I go back to our world-class controller. So I hope you like this. OK, I'm going to switch gears a little bit. I mentioned that the M series, there's a bunch of firsts on the Agilex M series. One of the firsts is the first FPGA to provide 1 terabyte of memory bandwidth. That is 4 terabits per side, 4 in the north, 4 in the south. Architecturally, we chose this approach. We prefer it from how the competitor goes at this. they have chosen to put HBM both on one side, and they have chosen to load that onto a NOC that is a fraction of the bandwidth capacity of this NOC that we're providing on Agilex. So what we have here is we're breaking the massive bandwidth problem in half here into a north side and a south side. This massive bandwidth necessitates a hardened network on chip, and that is a hard distribution of the 2 by 4 terabits. You see a horizontal switch NOC, which spreads read and write axial traffic across left and right. And then we have a custom vertical NOC, pushes that read data to exactly where you want it to the M20Ks, without consuming routing resources. The NOC is a full axial crossbar capability and connectivity from any of the fabric accessible, 20 fabric accessible initiators to any of the 24 targets per side. And with that, it presents a uniform view of your HBM and your DDR memory. And this mock-up shows HBM with DDR5 DIMMs. Okay, so I'm going to wrap up my section and talk about your developer experience. We've made several enhancements in the EMIF tool, the external memory interface IP generation tool. It's way more, it's more lightweight today because we've designed it per protocol. And because it's designed per protocol, we're achieving 250x per click response time improvement over prior generations, and 31x faster IP generation, which means you get the simulation faster and you shorten your time to market. It's more intuitive. So now you can pull down, you can see on the right-hand side, you can pull down your JEDEC bin selection, and it will auto-populate all those complex controller parameters that can be overwhelming. And then you can go into advanced mode and go in and tune those parameters based on the specific DRAM vendor you may have chosen. The new i96B architecture enables a more simplified per-bank calibration IP. And finally, the NOC is seamlessly integrated with the HBM IP. And the HBM IP itself comes out of the box as an example design, which is fully featured and highly configurable. So now, I'm really excited to welcome up Thomas Summers, who is, if you've missed the beginning, serial entrepreneur, CEO of Positron AI. And he's going to talk about Atlas, which is his transformer, i.e. large language model inference server solution. And he's going to talk about how Agilex memory has been a huge differentiator for his solution. Welcome, Thomas.
Thanks, Terry. I'll grab that for me. Thank you. Hi, everyone. I'm Thomas Summers, founder and CEO of Positron AI. For the past year and a half, we've been developing a transformer inference accelerator, and that is in the form of utilizing the Agilex AGM039, so the Agilex 7M series FPGA that integrates HBM2E. That gives us the actual bandwidth necessary as transformers are memory-bound workload. So with that, we've been able to achieve, and these numbers are actually a bit old, but you can come by the demo at 4 o'clock and see the latest numbers. But in this example, for a customer running mixed roll 8x7B, which is a total of 8 7 billion parameter experts, so about 56 billion total parameters, able to achieve over 100 tokens per second per user, and compared to an NVIDIA DGX H100-based solution, having over 6x monetizable density gain. So I'll also show a quick demo of exactly that running. You'll be able to see if it starts. There it goes. You'll be able to see a newer version of this at the booth later. And with it, you'll see on the left-hand side 2 H100s running versus 2 of our accelerators. This is running the MMLU benchmark, so a very common benchmark for being able to compare the capabilities of 2 different models, but here we're showing it running the same model, but with us having about 3x greater performance for mixed roll and using about 1/10 of the power. The demo later is with the Llama 3.1 a 7 billion parameter family. Yeah. So now talk actually about the tech of it. So in terms of our product roadmap, so yeah, we're 18-month-old, 21-person startup, but we actually just shipped our first production hardware to a customer last month. And now have about 8 customers currently evaluating our hardware. But we're shipping Agilex 7M today. I believe we're the first company to actually publicly announce that. And with that, we're having 8 cards in a 4U server chassis, so having a total of over 256 gigabytes of HBM2E and delivering over 5 terabytes per second of total memory bandwidth. That's able to support models greater than 500 billion parameters, and we're able to do that and selling at a price less than half of NVIDIA's DGX H100. With our current software release, you can see that we have about a 3x performance per dollar and 4x performance per watt advantage. And in successive software releases over the next about 9 months, we're going to be able to more than double that with the exact same hardware. Early next year, we're going to be having a new, smaller form factor with 4 of the Agilex devices that also extends the ability to have up to 512 gigabytes of DDR5 directly attached to each FPGA. It's in a 2U form factor, 4 devices instead of 8. So from a per FPGA perspective, same density per rack unit. But that addition of DDR5, which is also really unique with the Agilex 7M, is the fact that we can greatly expand capacity, not necessarily for increasing the actual model size, but being able to extend the context length. So if you imagine, today's models, if we look at like Llama 405B, which we see as a really amazing open source model competitive with OpenAI's GPT-4 4.0 for applications like programming, but the context length for it is at like 128,000 tokens. So you can think of that as being like a small software project. But actually unlocking and being able to have up to 2 terabytes of DDR5 directly attached to those FPGAs in the Atlas system next year, we can actually support context lengths in the millions of tokens. So that's something that can actually enable companies to have their entire code base directly visible by that language model. So super unique and something that simply can't be done on GPUs where, if you want more than, today's 80 gigabytes of HBM that's attached to a H100, you've got to just buy more GPUs. So we see that ability to scale out, or I should say scale up the memory system per device, and then with networking capabilities, be able to scale out to multiple systems. So on both of these systems today, each FPGA has 3 400 gig QSFP interfaces. And with that, we're able to scale out with tensor, pipeline, and expert parallelism. So you can actually scale the performance and capabilities of the model beyond just a single server node. Now, I guess I'll go a little bit into why we actually chose Agilex. So as Terry was saying earlier, the memory system is the fundamental bottleneck for transformer workloads. And so for us, when we were choosing FPGA vendors last year, it really came down to who had the best memory system. And the fundamental thing for Agilex 7M is not only just having the HBM, which the other company has, but actually being able to utilize it. So things like the fabric knock is absolutely critical to be able to actually unlock the performance of the device. We've got plenty of DSPs in that in our systolic array that we have, but fundamentally you're not going to be able to utilize them if you can't actually get memory to that. So the fabric knock and allowing direct connection to all the M20Ks is the fundamental bottleneck for being able to scale out the solution, and the Agilex 7M was able to solve that for us. Yeah, that's about it. Thanks, Terry.
All right, thank you, Thomas. All right, we're wrapping up. So, I'd ask of everyone here is take advantage of the EMIF IPE. Check out the latest Quartus Prime Pro software.
Altera, accelerating innovators.